I'm Adolph Oliver, and this lesson is on factors. And the first thing we want to know about factors, there are two different varieties of these. Okay, the first we're going to talk about is what I often call regular factors, but when folks mention it, they just mention the name factors all by itself. Now we'll contrast that with prime factors later on, but there's no mention of prime here, so these are just the regular factors. Now, what are regular factors? Well, they're numbers that can divide evenly into the original number that you start with. Now, what do we mean by divide evenly? Well, it divides in with no remainder. Let's give an example here. There's a nice systematic process you can follow. Let's say that our starting number is 18. Okay, well, the first thing I'm going to write down is that I can make 18 by going 1 times 18. You can always take 1 times the number, so this is always your starting point. Now, what you do, notice, of course, that both 1 and 18 divide evenly into 18, but to progress on, you start increasing this 1 here, 1 at a time, and any number you get that divides evenly into 18, you put it in your list. Well, the next number we try is 2. 2 divides evenly into 18. And we know 2 times 9 works. Okay, these are both factors. Well, let's continue on here. The next thing we try would be 3. 3 divides even to 18. 3 times 6 is 18. So far we've got all of these guys as factors of 18. Now, the next number we try after 3 would be 4. But 4 does not divide evenly into 18, so we don't put it in our list here. The next thing we try is 5. 5 doesn't work either. The next thing after that we try is 6, but this tells you when you can stop because we'd be trying 6 here, but notice I already got 6 over here. So once you get to the point where the next number you're going to try on this side happens to equal one of the guys you've already hit, you don't have to go any further because all the larger guys you've already gotten up this side. So this is a nice method to go through step one at a time. Anybody that divides evenly into your original number, put them in the list. Anybody that doesn't, skip over and keep going. And when you finally try someone who equals somebody you've got over in the right side already, you can stop. Well, these are all the factors then of 18. And what we can do is make a list of these. In mathematics, we often include multiple answers inside curly brackets like this. You'll see this quite often. And what's nice to do is put these guys right in order to make them look nice and pretty. So for instance, 1 is a factor, and then we have 2, and then 3, and then 6, and then 9, and finally 18. So what do we end up with here? The number 18 has a total of 1, 2, 3, 4, 5, 6 different factors. These are the only numbers that will divide evenly into 18, and factors like this we'll be using later on in some of the future calculations we'll be making in the algebra. Well, to go and understand the second group of factors, I mentioned that word prime. What we have to first do is talk about what we mean by a prime. So, here's the first key. Prime numbers have only 2 of those regular factors, the number 1 and their own number itself. What's a classic example of a prime number? Well, how about 7? All you can do with 7 in regular factors is 1 times 7. There are no other 2 numbers that you can multiply together to get 7. And of course that means there's no others that will divide evenly into it. So 7 has only 2 factors. That makes it a prime number. Now, numbers that are not prime are called composite. Well, our example that we had up above of 18 is a classic example of a composite number, because we saw that 18 has 1, 2, 3, 4, 5, 6 different factors. So 18 down below here we can say is an example of a composite number. it has more than 2 factors. Okay, so numbers can always be broken into either composite numbers that have more than 2 factors or prime numbers that have only 2. And of course, the key with primes is the 2 numbers are 1 and the number itself. Now notice the idea here. Primes cannot be broken down into smaller things. 7 remains 7 here. 1 times 7, we don't get anything smaller. But the 18 up here, a composite number, can be broken into smaller numbers, like 2 times 9 or 3 times 6. So one of the important ideas we see about the whole composite business here is that composite numbers can be broken into smaller pieces, whereas prime numbers cannot be. Because of that, prime numbers play an important role. And the next thing we want to talk about is how we can find these prime numbers, and we'll use what's known as a prime number sieve here to find the primes up to, say, about 30 here. Now, here's the process. This sieve business has been known for a long time, and we'll start thinking about the number 1. Now, number 1 is not even a prime number. Why? Because the only thing we can do with 1, if I write it up above here, is 1 times 1 is, of course, what 1 equals to. There are the 2 factors, but they're the same. So, in fact, 1 has officially only 1 factor, 1 itself. And because of that, we leave it out of the whole prime business. I'll just exit out right there. Okay, now let's show you how this works as we move on. Let's consider 2. Well, the only thing we can do with 2 is 1 times 2. That means, of course, that 2 is prime. So I'll go ahead and circle it. But now, here's where the power of the sieve comes in. All of the multiples of 2 going on from here are not prime. Well, why is that? Think of number 4 here. Besides 1 times 4, it's also 2 times 2. In other words, 4 has 2 as a factor, and once you get that third factor, remember 1 and 4 are the first 2, 2 would be the third. Once you get that third factor, it's not prime. So we knock out 4, and by the same reasoning, we can knock out 6 and 8 and 10 and 12 and 14 and 16 and 18 and 20, 22, 24, 26, 28, and 30. All of the ones I've just crossed out all have more than 2 factors, and that makes them not prime. Well, you begin to see the power of the sieve here. We've just knocked out half of all the remaining numbers. You could, of course, make this go up higher than 30, but we usually only need to know primes up to about 30. Okay, let's take a look at the next number, 3. Well, the only thing you can do with 3 is 1 times 3, so that means it is also prime. But just like we did with 2, we can now knock out all the multiples of 3, because any multiple of 3 will also have 3 as a factor, and that means it has more than a total of 2. So let's take a look. Many of these we've already knocked out. We already knocked out 6, but now we can knock out 9. We earlier got 12, but there goes 15. 18 we got earlier, but now we get 21. 24 we got earlier, and now we get 27. So again, we see the power of how this sieve works. Well, very quickly, we're getting just about down to prime numbers here. Let's do the same game here with number 5. 5, of course, is prime. All you can do is 1 times 5, so it's prime. And let's see if there are any multiples of 5 that we haven't knocked out already. We already knocked out 10. We already knocked out 15. We already knocked out 20. There is one here. 25 we can knock out, and of course we already got 30. Well, I think at this stage, since we're only going up to 30, I think all the guys that are left here are all prime numbers, and I don't think there's any more of their multiples we can knock out. So let's circle them. 7 is prime. All you can do is 1 times 7. 11 is also prime. 1 times 11. and similar for 13 and 17 and 19 and 23 and 29. Okay, all of these guys that I've circled are all the primes up to 30. Well, from this little demonstration we've done here, one of the things you see real quick is that the first prime number is 2, and 2 is the only even prime number. So in terms of primes, all that exist, there's only one that's even. The first one, the number is 2. After that, all the primes that exist are all odds, but not all odds are primes. Okay, for instance, 3, 5, and 7 are prime, but 9 isn't, because besides 1 times 9, you can also do 3 times 3. But then 11 and 13 and not 15, and so on. So this gives you another way that you can work up the primes, up to about 30 here. All you have to remember is the first prime number that exists is 2. It's the only even one. And then after that, just think of all the odds. Well, if you find an odd that has more than 2 factors, you get rid of it. Well, 3 is all you can do is 1 times 3. 5, all you can do is 1 times 5. 7, all you can do is 1 times 7. But 9, besides 1 times 9, you can do 3 times 3. That's why you kick out 9. Well, you can continue that with all the rest. For instance, 15 you'd kick out because besides 1 times 15, it also has 3 times 5. So, knowing the prime numbers up to about 30 is important because we're going to use that when we talk about how to find prime factors. Now remember, we've had regular factors, no mention of the word prime, but now what we're going to do is find the prime factors of a number, and we're going to use the consecutive primes, take them in order, 2, 3, 5, 7, as we just found in the sieve, and we're going to use what's known as a factor tree to come up with these prime factors. Let's visit our original 18, but now instead of finding regular factors for it, we're going to find the prime factors. Well, if we do this factor tree approach, I put a couple of branches down underneath 18. These kind of look like tree branches, so that's why folks call this a factor tree. And here's the idea. We're going to put at the end of these branches numbers that multiply together to give us this guy on top. But to make it work nice, we're going to do the primes in consecutive order. In other words, start with the lowest prime and see if it divides evenly into 18. Well, 2 certainly does. Okay, since 18 is even, we know 2 will divide into it. So what do we put over here? Well, 2 times what equals 18? 2 times 9. Now, if you put the prime on the left like we've done here, there's no need to put any more branches under it because it's prime and you can't break it anything smaller. But over here in the right side, the 9 is not prime, it's a composite number, so we need to break it down further. So put a couple branches down for it. Now 9, of course, is not even, it's odd, so 2 will not divide into 9. So we move up to the next prime number. Remember, after 2, the next prime number is 3. Well, does 3 divide evenly into 9? It sure does. And what do we put over here so that these two multiply together to give me 9? Well, this has to be 3 over here. So what we end up with now, these guys are primes and this guy is prime. So once you have primes at the end of all your branches, you don't have to go any further. You've gone as far as you can. These numbers cannot be broken into anything smaller. But what you do have to do is put them back together to indicate what the prime factors are, or as folks often say, the prime factorization of 18. Now when you write this, you want to use exponents if there are any of the primes that repeat more than once. So, and put them in order. So we've got a single 2 here. You could put an exponent 1 up here, but most folks don't bother doing that. And then a multiplication dot here. And we've got a pair of 3s. Well, that's 3 times 3, or 3 squared. So there is the prime factorization of 18 as we found it by this factor tree, and using the prime numbers in order makes the results come out nice here. We've got them all nice in order. Here's the 2 and here's the 3 squared. And of course, we want to double check this to make sure that it multiplies back to 18. Well, to check it, the 2 is just 2, but the 3 squared would officially be 9, and 2 times 9 does indeed equal 18. So we see that this is indeed our correct prime factorization. Well, the thing to remember here is the difference between the regular primes. Okay, those are the cases where you just have all of the numbers that divide evenly into it, and the prime factors where you end up with primes that have to multiply together to give you the original number. Well, let's now start working some examples of these to get a little practice on it. Here's our first one coming up. List all the factors of 24. Now notice there's no mention of prime here. We're just talking about regular factors. So you know in that case you can play this game of what two numbers multiply together to give you 24. And of course the thing you always want to start with is 1 times the number itself. So here we have 1 times 24. Now, remember how this game gets played. You increase the guy on the left, the 1 here, 1 at a time, and anybody that divides evenly into the original number, you put it in the list. Okay, well, the next number would be 2. 2 does go into 24. And what do we have to multiply 2 by to make 24? Well, 12. So these are the next factors we have. Well, the next guy we try is 3. 3, of course, works. 3 times 8. The next one we try is 4. 4 also works. 4 times 6. The next guy we try would be 5. Well, 5 does not divide evenly into 24, so we skip over it. The next one we try after that would be 6, but we already hit 6 here, so we know we can stop. Now, just list all the factors in order like this, and again, very commonly, we put them in curly brackets like this to indicate that they're all the answers. This would be the set of all the answers. Put them in and separate them by commas. 1, 2, 3, 4. Then we have 6 and 8, and then 12, and then 24. Okay, these are all the regular factors of 24. There's 1, 2, 3, 4, 5, 6, 7, 8 of them. These are the only numbers that will divide evenly into 24. They are the regular factors of 24. Okay, well, let's look at another example here. We want all the factors of 30. Now, once again, there's no mention of prime here, so we're not using that factor tree. Instead, we start out with 1 times the number. So since it's 30, 1 times 30. Now, we increase this 1 at a time. Does 2 go evenly into 30? Yes, it does. 2 times 15. The next number we try is 3. Well, 3 sure works. 3 times 10. Next number we try is 4. That doesn't work. But 5 does. 5 times 6. And the next number we try would, after 5, would be 6. But since we already got the 6 here, we can stop. Now again, it's just a matter of listing all of these. Let's do it again in our curly brackets here. 1, 2, 3, 5, 6, 10, 15, and 30. This is the set of all of the regular factors of 30, and we got them by playing this 2-number game. It works nice because we make sure we don't miss anybody, and of course we always know when to stop. When the next number we try here is already shown up here, we have all the others going up this side. Okay, well, let's take a look at doing this whole process with 26. Okay, we can always start out with 1 times the number. That's always going to work for us. And since 26 is even, we know that 2 works. 2 times 13. But after this, I don't think we're going to find much that works, because 3 won't go in, 4 won't, 5 won't, 6 won't, 7 or 8 or 9 or 10 or 11 or 12. 13 will, but guess what? We've already got 13 here. So the factors of 26, the regular factors, are a much smaller list here. Only 1, 2, 13, and 26. These are the only factors of 26. Okay, well, let's take a look at another example here of regular factors. Again, notice no mention of prime here. And we're starting out with 29. Now, of course, we know we can always do 1 times the number, so there it is. But after that, I don't think there's anything else that'll work, because if you remember, 29 is a prime number, and nothing else going all the way up to 29 will divide evenly into 29, and of course we already have the 29 here. So when you run into a prime number, it should be no surprise that you only have 2 factors. Remember, that's the definition of what a prime number is. And so in this case, only 1 and 29 are the only ones that would work. Okay, let's move on now to the prime factors. And the way this is often indicated is we want the prime factorization of 15. Now, there are many different ways that you can come up with the prime factors, but we've introduced you guys to the factor tree, and so that's what we'll make use of here. I put a couple of branches down, and then I start thinking of the primes in order. The lowest prime number is 2. Does 2 divide into 15? No. So guess what? We can try the next prime. The next prime is 3. Does 3 divide into 15? It certainly does. So I put 3 at the end of this branch. Okay, that's a prime number. Well, 3 times what equals 15? 3 times 5. Well, guess what? 5 is also prime. It doesn't do me any good to put branches underneath it, because it's as small as it can get. So in this particular case, we found the prime factorization really quick. It's just 3 times 5. They're both to the first power. So there we go. And of course, 3 times 5 does indeed equal 15. Okay, let's look at a number that's a little bit larger here. Let's say we want to have the prime factorization of 64. Well, we're going to do our factor tree again here. Here's the first 2 branches. Now, if your original number is even, you know that it's got at least 1 2 in it. So let's factor out that first 2 here. And 2 times what equals 64? Well, 2 times 32. Now again, no need to put branches under the 2. It is prime and can't be split anything smaller, but that's not the case with 32 here. So we continue our branches over here. Now 32 is still even. So while our number is even, keep pulling out 2's. Well, 2 times what equals 32? 2 times 16. Well, guess what? 16 is also divisible by 2, so that means it's got another 2 in itself. 2 times what is 16? 2 times 8. Well, 8 also is even, so it has a 2 in it, so we keep pulling 2's out. 2 times 4 is 8. Well, guess what? 4 is still even, so we keep pulling 2's out of it here. Put a couple of branches down. Well, 2 times what equals 4? 2 times 2. Well, we finally got to the point where the number in our bottom right is prime. We're done. Boy, we ended up with a whole bunch of 2's here when we started out with this 64. Let's slide it back and take a look. Let's count how many we got here. Here's 1, 2, 3, 4, 5, and the last one here is 6. So what does 64 equal? Remember, you have to put these all together. 2 to the 6th power. So if you have a total of 6 2's and you multiply those 6 2's all together, what you'll get is 64. Now, as we go along in the algebra, we're going to start getting some letters in here. Well, the letters tend to be easier to work with. It's primarily the numbers that we have to do the prime factorization on. So in this example, we know we've got an n here to the first power, but what we have to do is figure out what the prime factorization of the 75 is. Okay, well, here we go. First prime number we always try is 2, but we know 2 won't work because 75 is odd and 2 doesn't divide into an odd number. Now, of course, you see that 5 is going to work, but resist that because you want to take the numbers, the primes, in consecutive order so you have them all lined up nice and pretty when you go get your final answer. You may remember a way of being able to tell if a number is divisible by 3. This trick only works for 3, and here it is. Add the digits together. 7 and 5 gives me 12. Well, if the sum of the digits is divisible by 3, the whole number is divisible by 3. So that means there's a 3 in 75, so I can put my 3 down here. And now, 3 times what equals 75? Well, 3 times 25. Well, the sum of the digits now is 7. 3 does not go into 7, so there's no 3's in 25. So now we'd go up and try the next highest prime. The next highest prime after 3 is 5. And of course, 5 divides into anybody that ends in 0 or 5, so there's definitely a 5 in 25. And the second branch over here, what do we have to multiply 5 by to make 25? Well, 5 again. So, what does 75 equal in once we've factored it? 3 times 5 times 5. Well, we have to indicate what the final prime factorization is of 75n. For the number, we've got a single 3 times 5 squared times, of course, the n to the first power. So there it is. The variables are easy. It's the numbers that take the work when you do this prime factorization. Okay, let's look at one final answer here. This problem, give the prime factorization of 94x cubed. Now again, the variable's easy. We're just going to have x cubed. It's basically factored already. The 94 is what's going to take the work. So let's put our first set of branches down. Here we go. Okay, well, 94 is even, so that means we can pull a 2 out of it. Remember, we always start with the lowest prime, which is 2. Anytime we have an even number, we know we can get a 2 out of it. Okay, well, let's see. 2 times what equals 94? Well, 2 times 47 equals 94. Now, 47. If we tried to put some branches under that to see what we could do, well, it's not even, so that means there's no 2's in it. The next thing we try is 3. Well, the sum of the digits is 11. 3 doesn't divide into 11, so that means there's no 3's. The next thing we try is 5. Well, it doesn't end in 0, 5, so there's no 5's. The next prime would be 7. Well, 7 doesn't divide into 47. If it was 49, we'd be in business. Well, pretty quick, we're going to find out here as we keep trying. I mean, the next prime would be 11. That doesn't work. 13 doesn't work. In fact, 47 itself happens to be prime. It can't be broken into anything smaller, so once you keep trying things and figure that out, you'll see then that these last branches were not needed because 47 is prime and cannot be broken into anything smaller. So, that being the case, here's the only thing we can do for the prime factorization of 94x cubed. We know it's 2 times 47 times, don't forget the x cubed, and of course x to the third power. So there is our prime factorization of 94x cubed.